We have recently seen some beautiful methods for linear classification, logistic regression, the perceptron algorithm, and support vector machines. But we've only talked about the binary case, where the possible labels are +1 or -1. What happens when there are more classes? How can we accommodate them? So we'll see that there's a simple unifying formalism that lets us extend all three of these methods to multiclass. And we'll look at them one by one. So in this class, we've studied all sorts of different methods for classification, and some of them are inherently multiclass. Nearest neighbor, for instance. It just automatically adapts to however many classes there are. You don't need to do anything special at all. Generative models are also inherently multiclass. You just fit a Gaussian or some other distribution to each individual class, and that's it. Nothing else needs to be done. Linear classifiers, on the other hand, seem a little bit tricky. After all, when you have a line, there are only two sides to it. So how can we possibly accommodate more classes? So to get the main idea, let's think back to Gaussian generative models. What we were doing there was to fit a Gaussian to each class. So maybe a Gaussian for class 1, another Gaussian to class 2, another Gaussian to class 3, another one for class 4, and so on. We observed then that the log of the Gaussian density is a quadratic function. And so effectively, each class has got its own quadratic function. When a new point comes along, each class evaluates its quadratic function, and the one with the highest value is the winner. That's the label we predict. So we can do something similar to this for linear classification. We can let each class have its own linear function. Okay, so let's see what that means. So let's say we have data in d-dimensional space. So our data points x, y, and rd. And let's say that the labels now have k possible values, say 1, 2, all the way to class number k. We will let each class have its own linear function. Okay, so class 1 has some linear function. Let's call it w1 dot x plus b1. And here w1 is a vector in d-dimensional space, and b1 is just an offset, just a number. Class 2 has its own linear function, say w2 dot x plus b2, all the way to class k, say wk dot x plus bk. And now, when a new point comes along, when a new point x arrives, every class evaluates its linear function, and the one with the largest value is the winner, and that's the label we predict. Okay? So let's see how this works out for logistic regression. So for binary logistic regression, which is the case we studied before, if you remember, we just had one linear function, w dot x plus b. And for any given point x, the probability that y equals 1 was given by this formula over here. Now let's move to the case where we have k possible labels, 1 through k. We'll now have a linear function for each label. So for label 1, we have w1, b1. For label 2, w2, b2. For label k, wk, bk. And for any given point x, the probability that the label is j, the probability that y equals j, is going to be proportional to e raised to the jth linear function, wj dot x plus bj. Okay, so the higher this linear function, the larger the value of this function, the more likely it is that the label is j. Okay, so we said proportional to. What is the exact formula for the probability? Well, we just need these to add up to 1. Okay, so we just need to normalize. So the probability that y is j given x is exactly that term up there, e to the wj dot x plus bj. And now we normalize it. So we divide it by the term for class 1 plus the term for class 2 all the way to the term for class k. Okay, so that's the probability that y equals j given x. Now, what label would we predict for x? Well, the one for which this function is the highest, the one for which wj dot x plus bj is largest, in other words, the argmax of this. Okay, and that's it. So here's a summary over here of our prediction rule and our model. How about learning? So let's say we have a training set, x1, y1, all the way through xn, yn. How do we learn these k linear functions? Well, we'll do exactly what we did in the binary case. We'll just pick the parameters that maximize the likelihood of the data. That is, that maximize the probability of the first data point times the probability of the second data point all the way to the probability of the nth data point. Okay, so that's this function over here. And as usual, products are a little bit tricky to deal with, so we can just take the logarithm to make it into a sum. And if we want to make it into a minimization problem, we can just stick a minus sign in front. Okay, and when we do that, we end up with a convex minimization problem. In other words, it's a problem that's quite easy to solve, and in practice, we'll just hand the data over to a package which will then return the solution to us. Okay, so multi-class logistic regression is not a problem at all. Now let's move on to the perceptron algorithm. That was just 4 lines of code. Can we somehow adapt the perceptron to deal with multiple classes? And it turns out that it's actually really simple to do so. Here's the modified algorithm. Okay, also very short. So we have a training set, x1, y1, all the way through xn, yn. And as usual, we begin by setting all the parameters to 0, by setting all the linear functions to 0. In this case, we have k of them. Then we start going through the data set, okay? And each time we come to a point that's misclassified, we do a little update. So we go through the data, and let's say that we arrive at a particular point xy. The first thing we have to do is to figure out what label we would predict on x given our current parameters. Okay? And that label is simply the label j that maximizes wj.x plus bj, where the w's and b's are our current parameter values. Okay, so let's say that the label we'd predict is y hat. Now, if that's the correct label, if y hat equals y, then we don't have to do anything. But if we predicted the wrong label, if y hat is not equal to y, then we have to update the parameters. But which parameters do we update? We have k different linear functions. Well, we're only going to update 2 out of the k functions. We're going to update the function for the correct label and the function for the label that we actually predicted. And both of these updates are very simple. Okay, so for the correct label, we simply add x to the w vector and increment b. For the label we predicted, we just subtract x from the w vector and decrement b. And that's it, the multi-class perceptron algorithm. Okay, so let's see it at work on a simple data set. So here is some data in 2 dimensions and with 3 classes. We have the black triangles, the blue stars, and the red circles. What does multi-class perceptron do on this? Well, this is the boundary that it finds. It perfectly classifies the data. Okay? Now, as you can see, the boundary that it finds is made up of 3 linear pieces. There's this piece over here, this piece over here, and this piece over here. Okay, and basically it keeps cycling through the data until it finds this perfect classifier, at which point it immediately halts. It does not, for instance, try to optimize the boundary further, for instance, by trying to center the boundary or by trying to maximize the margin in some way. Okay, so that makes us wonder, what about the support vector machine? Can we make that multi-class as well? And indeed we can, and it's quite simple. Okay, here is the convex program for multi-class support vector machine. Okay, so as before, let's say we have a training set, x1, y1 through xn, yn. As usual, we want to minimize the norm of w squared. But in this case, we have k different w's. So what we're minimizing is the sum of all of their squared norms. As usual, with the soft margin SVM, we have a slack parameter for each data point. Now, if you recall, the function of this was to allow us to violate some of the constraints, because, for example, it might not be possible to perfectly classify all of the training data. So the slack parameter allows us to violate some of these constraints, but we don't want too much violation, and so we include the sum of the slack variables in the function that we want to minimize. Okay, and that remains unchanged from before, from the soft margin SVM. And then over here we have the constraints that say that we want the data points to be classified correctly. So what exactly are these constraints? Let's take a look. Let's say we have a particular data point, xi, yi. Now there are k possible labels. In order for this point to be correctly classified, we need the linear function for the correct label to beat out the linear function for any of the incorrect labels. Okay? So for the linear function for y sub I has to be greater than the linear function for the k minus 1 other labels, the y's that are not equal to y sub I. Okay? So if we write out this condition, what we have is that the correct linear function, which is w of y sub I, the w for the correct label, dot x sub I plus b of y sub I, should exceed any of the wrong linear functions. So wy dot x sub I plus by for any of the labels that is incorrect. This is the condition that says that all the points are perfectly classified. Now, as we did before, we can equivalently insist that actually the correct label exceeds the incorrect labels by 1. Okay? And we can do this by simply rescaling the w's and b's appropriately. Okay? So this is another way of saying that all the points are correctly classified. Now, of course, it might not be possible to correctly classify all the points, so we do have to allow a little bit of slack, and that's where we include the slack variable psi sub I. Okay, so these are our final constraints, and this is exactly the inequality we have over here, just shifted around a little bit. Okay, so this is the convex program for the multi-class SVM. So let's see it at work. This is the iris dataset, which we've talked about before. I've chosen two of the 4 features. There are 3 classes, and it's clear that the data is not linearly separable. So in particular, we would not be able to run the perceptron algorithm on this. Okay, but let's see what the multi-class soft margin SVM does. This is the boundary it finds. It does a very good job. As usual, it is a very competent classifier. So let's end with a little bit of a small question. Okay, so this was the convex program for the multi-class soft margin SVM. How many variables do we have here, and how many constraints? Let's see if we can count these. Okay, so the variables are the W's. Okay, so W1 through WK. How many parameters do we have there? Well, each of them is a d-dimensional vector, so it's a total of kd parameters. Our variables also include b1 through bk. Each of them is a number, so that's k parameters. And then we have the slack variables, psi1 through psi n, so n parameters. So the total number of variables is kd plus k plus n. How about constraints? How many constraints do we have over here? Okay, so let's see. For each point, we need the correct label to beat out the k minus 1 incorrect labels. So for each point, we have k minus 1 constraints. So the total number of constraints, since there are n data points, is n times k minus 1. Okay, and that's it. Okay, that's good for today. We've seen how we can extend our linear classification methods from binary to multi-class. It's really quite simple, and in one fell swoop, we were able to take care of logistic regression, perceptron, and the support vector machine. See you next time.